Okay. Chapter 2 is going to be very similar to Chapter 1 in that we are going to break it into different chapters. We'll go partway through the chapter and take a test, and then finish up the chapter and take a second test. It's a long chapter, just like Chapter 1 was. In fact, we only cover 3 chapters in this entire semester. So this one will take us the majority of the way. Chapter 3 is not as much. But again, it's going to look a lot like things you've seen before, because last year you were introduced to imaginary numbers. And that is kind of the theme of today, is imaginary numbers. But more specifically with combination of real numbers, which we then call them complex numbers. Today we're going to learn how to add, subtract, multiply, and divide complex numbers, dealing with square roots of negative numbers and all of the operations that go along with those, which then allows us to do things like solve a quadratic equation that has a negative under the radical, and how we simplify that all the way down. So, starting at the beginning, this is all based off of the imaginary number, I. And I know that I is a letter to us in our alphabet, but in math, I is a number. And its definition is here. That I equals the square root of negative 1. Now, we don't ever see that, and we would replace a negative square root with the letter I. We will see this show up a lot today, that I squared, and what we need to do is know that if I were to square both sides of this, that I get negative 1, and we will always replace. We will always replace I squared with a negative 1 in our problems. We will never have an I square at the end of our problem, or we're not done simplifying. Okay? So that's one that we will always be looking for. We are talking today specifically about complex numbers. And complex numbers, again, its definition is the combination of a real number and an imaginary number. And it will always be of the format A plus BI. When we are asked to give our answer as a complex solution, we will break it into those parts, real number plus imaginary number. I know it says A plus BI. That can be a minus there too if B happens to be a negative number. If I am forced to write things as a complex number, but it only has one part or the other, just the real part or just the imaginary part, we really can write it in that A plus BI. And it's just that if we're missing one of those, so A plus BI, 2I would be the imaginary part. If you're missing the part in front of that, it's just a 0. So if I had to be forced to write it all the way out as a complex number, the part you're missing is 0. Same thing on this one. Of the A and the BI, we have the real part. So if I'm missing the second part again, it would be 0 of those. We'd have a 0I. So I could make them look like complex numbers if it asked me to, because every number, real or imaginary, can work into that complex format. Most of what we're working with today will have both parts to it, real and imaginary. When we are working with adding or subtracting, it is no different than what you saw on page 1. So when it's adding and subtracting, you really can just kind of look at the I part of it as an X and treat it like terms. I know this kind of makes it seem a little more complex up there, but if we have a complex number A plus BI and then a second complex number C plus DI, you just match the real numbers together, the A and the C, and add those. You match the imaginary numbers together and add those. No different than we would have found our plain constants on our warm-up and our x's on our warm-up, and combine those like terms. When we are subtracting, again, no different than our warm-up or how we would have treated this had this been x's instead of i's, is that you have to remember to distribute the negative first, and then all we are doing is just combining like terms. Okay, so let's go ahead and look at an example of combining our like terms given two complex numbers. So it says perform the indicated operation, write the results in standard form. When it says write the results in standard form, that means our answer should look like A plus, how about A? Okay, it doesn't want me to write in that corner. Should look like A plus BI when we are all said and done. Maybe I can write in the middle here. Okay. So find my real numbers, 5 and 3. Combine those and I get a total of 8. Find my imaginary numbers, -2 and 3i. Combine those. -2 plus 3 would be a +1. You'll notice I will not write the 1 in front of the I. It's like I wouldn't write a 1 in front of an X. You can if you want to. It's not wrong. You just won't see it there usually. On the subtraction one, job number 1 is to distribute that negative through. So before we start combining our like terms here, I'm going to reorient my board. Okay, let's try this again. 2 plus 6i minus 12 plus I. Then I can start combining my like terms. Real numbers being 2 minus 12. 2 minus 12 is -10. My imaginary numbers would be 6i and 1i. 6 plus 1 would be 7i. Okay. All right. Any questions on the combining like terms? Okay. Then we move into the multiplication part of it. Initially, the multiplication part of it is going to look no different than multiplication would look again if they were x's. The only difference is when we are done, we are going to make sure that we find and replace all I squareds with -1. Okay, so when we are done, there should be no I squareds in our answer. That's the only difference that's between this and what we would have done if they had said x. So I start the same as I would have. I'm just distributing, so I'm going to take 7i times 2. I'm going to take 7i times -9i. I can multiply anything together, so even though these are not like terms, I can take 7i times 2 and get 14i. On this next one, 7 times -9 would be -63. I times I is I squared, and that's what we were talking about finding and replacing, is that I will not leave an I squared in my answer, as I will replace it with a -1. And then because I'm supposed to write my answer always as A plus BI, the real number will come first. -63 times -1 is going to be 63. Or another way of looking at this is your I squared is always going to change the sign, because multiplying by a -1 is always going to change the sign on that. So it's going to turn into a positive 63, and it's a positive 14i. Same thing with your FOIL. I've got 2 things times 2 things. I FOIL, and we don't change the fact that we FOIL. That will remain constant, even though they are i's instead of x's. The only thing I'll do is when I'm going to like clean it up at the end is I won't leave any I squareds in my answer. I will replace and combine my like terms. So we start with our first term here. 5 times 6 is 30. 5 times -7i would be -35i. 4i times 6, 24i. 4i times -7i, -28. I squared, and there's our find and replace. So I'm not going to leave that that I squared in there. I'll replace it with a -1. okay? Or again, understanding that as soon as I'm about to write down an I squared, it's just going to change the sign on that number. My good number sense people, you're going to be able to save yourself several steps of work here, because as soon as I go to write this, all I'm going to do is actually just change this sign here instead. I don't even necessarily have to replace it with the -1, because ultimately it's just going to turn that into a positive 28. Now I can go through and find all my like terms. My real numbers would be 30 and 28 for a total of 58. My imaginaries would be -35 and positive 24, which would be a -11i. And again, I'll always write it in the order real number plus imaginary number, a plus bi. Questions on that? All right. Moving into the division part of it, division is the only time that it is going to look quite a bit different than if they were just plain x's. And what we're going to use when we do the division to clean up our problem is what is called the conjugate of our complex number. Okay, so what is a conjugate? Because you're going to hear me use that word a lot. A conjugate, or the complex conjugate of our complex number a plus bi, you'll notice has the same two numbers a and b. It'll just change the sign that is between them. So if it was a plus bi to start with, your conjugate would be a minus bi. If it had started out as a negative, it would turn it into a positive. Now the next part of it is something you do need to understand and expect to happen, because if it doesn't happen, something went wrong, is that if we multiply conjugates together, that the result is always a real number. And what does real number mean? It means it has no I left in it, okay? So when I multiply my conjugates together, so how does that work? If I were to just use these sample numbers here, it would be my first number times my first number, and when I FOIL, which would be a squared. And then a times negative bi would be negative a times bi. And then a times bi would be a bi. And then here, b times b is b squared, negative b squared. And then this would be an I squared, okay? So a couple things are always going to stay the same when we do this. First of all, these two will always cancel. That's always going to happen because of how it's created. With the opposite signs in the middle, those middle terms will always cancel. This will get replaced with -1, which will turn this into the opposite sign. So it'll always end up turning this, or changing the sign. Okay? Which, when we do this then, I'll have that a squared here. This changes my sign and becomes a b squared. Notice no i's left, right? Because that I squared became a -1, changed the sign. So what will happen, again, with my really good number sense people, is you're going to be able to skip a whole lot of this work and know that your answer will always be the first number squared plus the second number squared. Or A and B. Okay, it will always be that way. And that can speed up your process a little bit. As long as you have multiplied by the correct thing, that should happen every single time. Okay, anyone still need this page? Okay, so how then do we utilize this when dividing? The reason, and I'm going to erase this here in just a second, maybe, if it switches pages on me here. I'm going to erase this in just a second, so you maybe don't want to show this, but When you guys were learning about radicals and simplifying radicals, you learned that you can't have something like this in the bottom, right? And we learned this whole rationalization process, right? Well, we really do have a radical in the bottom. In the bottom, it is 4 minus the square root of -1, which again, we wouldn't write as -1, but that's why we have to go through this process, because if there's an I, there's technically a radical in the denominator of our fraction. Okay, so you understand why we are cleaning this up. So, again, I would not write it as the square root of -1, but here's how we're going to go about cleaning this up so that I don't have any i's left, because if I just multiply by I, we're still going to have an I there. We will multiply top and bottom and top and bottom by the conjugate of the bottom, because that's ultimately what I'm trying to get the I out of. So the conjugate of the bottom of this one, again, it's got to be the same two numbers, 4 and 1, but we change the sign between them. So 4 plus 1i, and that's what we use for the top and the bottom. In the top, you are just going to have to FOIL. There's really no way around that, and it will probably remain an ugly complex number. Okay? So when I FOIL the top, we get what? 20 plus 5i plus 16i plus 4i squared, which I'm going to change to a -1, which changes the sign on my number, right? In the bottom, yes, I can FOIL that, right? If I want to continue to FOIL it instead of jump to our shortcut, I absolutely can, which would look like 16 plus 4i minus 4i minus I squared. Notice those middle terms are always going to cancel, always. And I squared I can replace with -1. Okay, so minus a -1 will become +1. Cleaning this up, again, also replacing this with a -1, we'd have -4. So 20 minus 4 would be where I'm getting this 16 from. 5i plus 16i is 21i. And then 16 plus 1 is 17. Okay, then the cleanup process, we will break over the common denominator and simplify to get our format a plus bi. So this is right now all together as one fraction, but when they ask me to write it in standard form, which is a plus bi, they are asking me to break that apart into the real number and the imaginary number. And so that break is going to happen right here at whatever my plus or minus is, and that will sit between my two fractions. But both of my fractions are going to get the common denominator that is down there. So I will have a 16 over 17, the plus that was between them. I will always slide the I out to the side here. So I have 2 over 17, I. You can leave the I in the numerator, that's fine. To me, it doesn't really matter. We'll have to learn a little bit about our My Math Lab and its particulars that it cares about. But this is your standard form right here. So there's our real number, 16 over 17, and your imaginary number is 2 over 17i. Questions for me on that? That's our only example of this, so I want to make sure that we don't have any questions before I move on. Multiply by your conjugate, clean it up, break into your real and imaginary. Two fractions over the same denominator. Okay, the last thing we're going to get into here is eventually being able to solve our quadratics or solve equations that have imaginaries as solutions. To do that, we have to talk about how to deal with working with radicals that have negatives in them. So first of all, when I'm working with radicals, I cannot add or subtract them together unless they are the exact same radical. These are not the exact same radical, right? So right now they would just stay separate from each other. However, I can simplify radicals. We have not talked a lot about simplifying radicals, but we've been kind of reminding ourselves of what that looks like here. When I simplify these, there are different techniques. I like to break it into the real and the imaginary. Start at half of the number that's in there and work your way down all of the perfect squares to see what the biggest perfect square is that would go into that number. 18, half of 18 is 9, which happens to be a perfect square, right? So that is the biggest perfect square that would go into 18. This still has to say 18, so I would say 2 stays inside. 9 times 2 is 18. I'll always put the negative in with the perfect square because it's going to change also. It's not going to stay inside my radical. So when we clean this up, just square root the 9 like normal. And then you're going to bring that negative out, and it's going to look like an I. And then your square root stays for the not perfect. So negative 9, square root of negative 9 comes to be 3i. And that square root of 2 stays a square root of 2. Do the same thing for the 8. Biggest perfect square would be 4 times 2 says 8. Put the negative with your perfect so that when I square root it, it comes out to look like an I. Now, because these are the same radical, it would be similar to seeing something that says like 3x minus 2x. Okay, that's not what it is, but it's kind of the same idea. They're like terms that I can now combine. So they all have the exact same thing all over there. So 3i minus 2i would be 1i. And we are just combining the square roots of 2 that we had up there. So it would be 1i square root of 2. Questions on that? Okay, this one is a little bit tricky, and I feel like there could be some confusion depending on how you attack this problem. But when we have something like this, first of all, do you recognize that we would have to write it twice and FOIL? Yeah. I think we can avoid some confusion if we also take a second and rewrite this as a simplified radical. There is no perfect square that goes into 3. So the square root of 3 will not change. But instead of leaving it as the negative inside, I'm going to slide that negative out front and call it I square root of 3. I wrote it twice, so we can now FOIL. Negative 1 times negative 1 is 1. Negative 1 times I squared of 3 would be negative I squared of 3. Same thing here. Negative 1 times I squared of 3 would be negative I squared of 3. And then we have I squared of 3. Ooh, this one's tricky. Let's look at this a little bit bigger here. I squared of 3 times I squared of 3. I times I would be I squared. What is square root of 3 times square root of 3? 3, right? So we would have here negative I squared, which is negative 1. Square root of 3 times square root of 3, which is 3. So combining my like terms, 1 minus 3 is negative 2. And negative 1 minus 1 would be negative 2 I square root of 3. Questions? Okay, our last example is going to be prepping us for the last thing we're going to talk about, which involves our quadratic formula. Okay, so we're looking at one that what you're seeing right now would be like our very last step of quadratic formula. We've put it all in there, we've like combined all those things. And what you're going to notice is, because our focus today is complex numbers, you're going to end up with a negative number inside the radical of that quadratic formula. Now, depending on our section, we might say, ooh, that's imaginary. There are no answers to this. But today we are really looking at imaginary numbers or complex numbers that involve imaginaries. And so when you see something like this, the first thing you're going to do is just zoom in on that radical and simplify it. Okay? Does anyone know biggest perfect square that goes into 12? 4. Again, still needs to say 12, so 4 times 3 is 12. I'm going to put the negative with my perfect here and go ahead and square root. Square root of 4 is 2. The negative comes out as an I. And I can now replace that where the 12 was in the original problem. So we start by just simplifying the radical. And then we're going to go ahead and write it in our A plus BI format, which means I'm going to break at the plus or minus. And I'm going to go give them both the common denominator. So it'll be a negative 14 over 2 and a 2i over 2. And actually, notice I'm going to slide the I always off to the side. So it'll be 2 squared of 3 over 2. I. And finally simplifying that, because 14 divided by 2 is 7. 2 over 2 is 1, square root of 3i. Now let's talk about this square root of 3i. If you look in your book, you will always see it written as square root of 3i. I will a lot of times write it as I square root of 3. And this is why. I just want to justify my decision to put the I in front. Typically, you put the coefficient in front of the letter instead of the vice versa like this. However, we have some people with sloppy handwriting. And is the I inside or outside the radical right there? Ish, right? It's kind of both, and it's not supposed to be. So if you follow how the book writes it, or they want you to type it in, you'll put the I second, but it's outside of the radical. So you need to very clearly make it outside the radical and not make it questionable. Do you understand what I'm saying? Or write the I in front of it. And I'm just fine if you handwrite your I in front of the radical instead of behind it. So I just want to tell you why I typically write the I in front of a radical instead of behind it, to avoid any confusion. Okay, our last conversation today is about finding solutions to quadratics that involve complex answers. And all that means is we're not going to get nice, pretty numbers, which means no factoring, okay? Because that's what I would have told you to do to start this, right? I would have said, hey, we've got an x squared, we've got a plain x, we've got a plain number, try factoring. And if it doesn't factor, then I would go to my quadratic formula. Knowing what we're doing today, expect a negative inside your radical, because we're dealing with complex numbers today, okay? So if you do not remember your quadratic formula, let's start there. Your quadratic formula looks like this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If you didn't know that, make sure it's in your notes. When we see the letters a, b, and c in there, a refers to the number that is in front of your x squared term. B refers to the coefficient of your x, plain x term. C is always the constant. It does have to be equal to 0, so make sure that you always have it equal to 0 before you start this process of identifying A's, B's, and C's. So using our example, A would be 1, B would be negative 2, C would be 2. Setting this up then, negative B. Because there's a negative in the formula and a negative on our B, you'll notice eventually that I'm going to write that as just a positive 2, negative, negative, plus or minus the square root of B squared minus 4 times A times C all over 2A. So getting your numbers in the correct spot with the correct signs is half the battle, and then the cleanup process starts. Like I said, today we're going to expect a negative inside our radical because the whole point of this section is complex numbers and looking at how we handle those. So cleaning this up, negative, negative turns into a positive 2. It will stay a plus or minus here. Inside my radical, negative 2 squared is actually a positive 4, but negative 4 times 1 times 2 is negative 8, which ultimately would give me negative 4. Now this radical is a perfect square, right? So we will be able to just square root it and not have a radical left there. Sometimes happens, sometimes doesn't. But square root of 4 is 2. Because of the negative, it'll be 2i. And then anytime we have both a real and an imaginary, we're going to break at the symbol and give them both our common denominator. In this case, that is a 2. So we're going to break at that plus or minus and give both the real and the imaginary part of that the denominator of 2. And I'm going to slide that I off to the side like I've done with every other problem. So 2 over 2. Keep that plus or minus between them. 2 over 2. Which means at the end of this, x equals 2 over 2 is 1, plus or minus. 2 over 2 is 1, which you can write, but you don't have to, I. And again, that's 2 answers, right? That's 1 plus I, and that's 1 minus I. Any questions for me? All right. We are going to skip over our check for understanding today because I want to get you guys your tests so you can see how you did before you get out of here this weekend. Your assignment while you are waiting in the interim to see your test is my math lab number 24.